So we'll go over two more examples here with the 4B homework. The first one, they're asking about the energy of a photon, and they're saying it has a frequency of 9.35 times 10 to the 21st. So remember, we actually have two equations. We have E equals HF, and we have C equals wavelength times frequency, or frequency times wavelength. So if they're asking for energy and they're giving us a frequency, which of those equations do you think we would want to use? Yeah, probably the top one, right? So I'm actually just going to plug it in. Remember, H is 6.626 times 10 to the negative 34th, and C is 3 times 10 to the 8th. So H times F and I get so when I put it in my calculator, trying to show it on the screen here, I get 6.19 times 10 to the negative 12th. So that is, that's Planck's constant. If you actually, I want to show you your conversion sheet. If you look at the bottom right of your conversion table, you'll actually find those two values down there. You have the speed of light, C, and then Planck's constant. They rounded it up to 6.63 times 10 to the 34th, but the actual, is that what you were asking? Because it's just rounded up from 6.626. So I misunderstood your question there. So what did I say? It was 6.19 times 10 to the negative 12th. Make sure you can do that on your own. Don't just trust me, because you might find test time that you watched me do it a bunch of times over and over again, but then didn't have it yourself. So does anybody have any questions on that one? So then I do want to look at the second one because it's a little more complicated. Now they're giving me a wavelength and they're asking me to find energy. So what do I do now? Because they're giving me the wavelength and they're asking me to find the energy. There's not one equation that I can use, right? But I can use this equation to convert wavelength to frequency, and then I can put that frequency in for the energy. So we'll do the bottom one first. Frequency is C divided by wavelength. We should know that from 4A. So it's 3 times 10 to the 8th divided by 4.89 times 10 to the negative 7th. So 3E8 divided by 4.89 E negative 7. And I get 6.13 times 10 to the 14th. That's not my answer. Did I say negative? No, positive 14. And remember, frequency is always measured in hertz. Energy is always measured in joules. Wavelength is always measured in meters. But now that I have the frequency, I can go back to just like I did in number 3. I know E is HF, so do 6.19 You can do 6.63 times 10 to the negative 34th times 6.13 times 10 to the 14th. We should get 6.13. Notice I'm not putting the times or the tens in, I'm just writing E. But I get 4.06 times 10 to the negative 19th. So 4.06 times 10 to the negative 19th joules. So that's how I would find energy in the two-step process. Does that make sense? Do we have any questions about either of those? Alright, so just some definitions. We talked about this when we were looking at the lamp. But the lowest energy state of an atom is a ground state. That'd be like if you were climbing a ladder, your lowest energy state would be the ground. And then you give yourself potential energy as you go up the ladder. Because obviously the further you go up, the more it would hurt as you fall. It's the same idea with the electrons. The further they go up the quote-unquote ladder, the more excited they are, the more energy they have. But anytime they have higher potential energy than the ground state, they're considered an excited state. So anytime they're on the ladder. Energy drinks. So when investigators passed an electric current through a vacuum tube of hydrogen at low temperature, or low pressure, they observed the emission gave a characteristic pink glow. Now, for those of you who are here, you can see it if we look at the lenses, but I'll put a picture up for those of you who are watching online. What we're seeing is we're lighting up a glass full of hydrogen, and it's going to look something like this, where it's going to glow pink, and then we look through a lens and we're going to see 4 distinct lines instead of what we normally see is a rainbow, a whole spectrum full of light. But with hydrogen, the only thing that we're going to see is 4 distinct lines. So this picture here kind of shows it. We're putting light through a prism, and we see that there's 4 distinct colors as a result. So there you go. But you should see something like this picture here. You should see a distinct red line, a distinct bluish line. Maybe you see a purple line, and there's technically a 4th one, but looking through the glasses, you can just barely see it if you can make it out up on the screen here. It's very faint, so you're likely not going to see the 4th line, but you at least see 3 distinct colors there. So that's what they noticed when they put hydrogen. They gave it electricity, and it shined 4 specific colors, and that was called the line emission spectrum. Go ahead and turn that off. Oh, I guess I do have a picture right there. I didn't have to look it up, but that's what you're seeing. We shine this light into a prism, and you see looks like maybe there's even 5 distinct bands that you could theoretically see. I did see that yellowish one in the picture, but that one is also really, really faint, so you probably didn't see it through the glasses. But what do we make of this? Because we know it happens. We see that when we light up hydrogen light, shine it through a prism, it gives us 4 distinct colors. But Bohr proposed a hydrogen atom model from that, and his idea was that because the electrons can only give off certain amounts of energy in the form of light, they must be only allowed to be in certain places called orbits. So think of the planets, like Earth can't go all over the place, Mars can't go all over the place. That's how he viewed the electrons, was that they're all orbiting the nucleus in their own path. So the higher out from the nucleus I go, the more energy the electron has. So then what happens is when an electron falls from an energy level, it's going to emit light, it's going to give off light, and that's what we just saw. But when we can also do the opposite. What I'm doing is I'm putting electricity in that lamp. I'm giving those atoms energy, and those many, many atoms are responding to that and getting excited to different levels. When I excite the electrons, when I excite the atoms, that's called absorption. It's absorbing the energy. So it can take in energy and go up energy levels, or it can go down energy levels by giving off energy. So we see emission versus absorption. And just to show you on a picture here, again, if I shine a certain amount of energy into the atom, the electron's going to go up an energy level. But if an electron's already at an energy level, and it falls down to the ground state, it's going to give off a particular color of light. Now notice, I could shine light that was slightly more energetic than this orange light here. And what would happen is the electron would go up maybe a little higher, but it would still fall back down to this energy level. It'd be like if you were trying to hit a golf ball up a hill. You can hit the golf ball higher than the hill, but it's still going to fall back down to the hill. So it's higher than when you started, but it's still lower than you hit it. So I can give it more energy, but it's just going to fall back down to here. If I give it enough energy, I can maybe get it up to the second energy level, but there's a certain frequency of light I would have to shine at it for it to absorb and reach that energy. So one last thing I want to show you is the hydrogen emission series. So notice there's different series that have fancy names that we don't have to memorize, but there's the Lyman series, the Balmer series, Paschen series, and the Brackett series. Each of these is representing different energy levels that the hydrogen atom can be in. And I give off specific frequencies of light for each time the electron can fall. It can go from the second to the first. Anytime it falls all the way down to the first energy level, that's in the Lyman series. But it could also fall from the third to the second, or any other energy level down to the second. And that's what they call the Balmer series. What I'd like you to see is the different colors of light. So this one shows it a little bit better. Notice the ones we're seeing are the Balmer series, where the electrons are going from either the third, the fourth, the fifth, the sixth energy level down to the second. Because we can't, notice the Paschen series, it's only infrared, and the Lyman series, it gives off UV. So we're only seeing some light. It's also giving off infrared and UV in the lamp as well. But any questions on what we went over today? We'll start up with section 2 tomorrow.